So Ambra is the Vice President for Research and Development at Vattenfall. You already heard that it's the largest power supplier in Sweden. Before that, and that's since last summer, and before that she spent around 15 years in the same company as me in ABB, and in between for 4 years she was with DNV, which is a provider of services in the energy sector. As you see from the slide, Ambra studied at University of Palermo in Italy, where she has a PhD in power engineering. And prior to joining industry, she worked at Chalmers University in Gothenburg here in Sweden as an associate professor in power systems. And she is a senior member of IEEE and board member of Power Circle and member of SIGRE, and something called Kraftkvinnorna. How do you translate to English?
Women in Power.
Women in Power, of course.
Thank you.
Please, Ambra, the stage is yours.
Thanks a lot, Alf, for the nice introduction. Good morning, everybody. How are you doing? Is everybody enjoying, are you enjoying the conference so far? Yes? Yes? Good? Very good. Nice round of applause here to the organizers. They fixed a very nicely, very nice technical program, very good venue. They also order perfect weather. You noticed that. I have been living in Sweden for more than 20 years. I can tell you this is not normal. So we do have good days in June, of course, and nice weather, but not this stable and this hot. So enjoy it while it lasts. And some of us were on a dinner on a boat yesterday. Who was on the boat? Okay, I was hoping more people, because then you would be tired, and as tired as I am. But I will try to do my best here. It sounded like a better idea yesterday before we came back at 11:30. But okay, so I can say something already. I was recommended to come clean. I have no equations in my slides, okay? So you can relax. And what I will try to do is to give an overview of the energy system in transition. So what is the energy transition and how that impacts the energy system we all live in, and the power system. And then, of course, I will have some examples that show how control and optimization come into play there. More and more, actually. Good. Yeah. So that's a bit what I meant to say, the summary of the talk. And first of all, I will say a few words about Vattenfall, because I know that many international guests, you may not be all familiar with our company. As said, we are the biggest energy producer in Sweden, but we are active in the all Northern Europe region. And we have about 21,000 employees in several countries, and are actually 100% owned by the Swedish state. But we work, of course, in the market like everybody else, all other utilities. And yeah, we have 8 million customers of electricity, but we also produce heat and gas. Maybe I have a little bit more on that later. And we also have the grid, power grid, distribution, and sub-transmission that we only have in Sweden, and with 1 million customers. Yeah, and since we are, as I said, we are active in Northern Europe, so also some other countries like France, Finland, where we have a smaller presence. But our main markets are Sweden, Netherlands, Germany, Denmark, and the UK. And then sometimes I show this just to give a perspective where our plants are. That tells a bit also the story. So we have, for example, nuclear that we built several years ago. I think you should be able to see now a couple of dots coming up. And we have, for example, 2 plants in Sweden where we are owner or co-owner. And another of our energy sources is hydropower, which, of course, everybody loves hydropower nowadays, right? It's green, renewable, but it's also controllable. And we have quite a lot also that in Sweden. But if you look at where we are investing most today for new build power plants, is, for example, much more in wind power. And that tells a bit of another story. I will turn the other ones off. And yeah, wind power instead, we are building quite a lot outside Sweden. In Sweden, we have land-based wind parks, but then we build a lot of offshore parks in UK, in Denmark, in the Netherlands. And I want to mention this last week, we had a new win of a license in the Netherlands. It's so new, I don't even have the slide, but that's a very nice project. We're going to build a 2 gigawatt wind park in the Netherlands combined with 1 gigawatt hydrogen electrolyzer. And also there is floating solar in between the wind turbines to better use the oil resource and the space. So it's quite an innovative, and the electrolyzer will be in the area of the Port of Rotterdam, and the hydrogen then will be used by the industries and the port around the Port of Rotterdam. So it's a very innovative project and an innovation tender, so to speak, from the Netherlands government. So all in all, if we just give you the picture, we produced last year 100 terawatt-hour, of which 1/3 is nuclear, 1/3 is hydro, a little bit more than 1/3, and the remaining third is wind and fossil-based, and we are trying to get out of that. We have reduced our emissions, carbon dioxide emissions, by more than 50% in the past 8 years, I believe. And we are continuing gradually getting out. And then maybe just this, maybe I've already said a bit. We are in production, so a lot our heritage is generation, but we also have the grid in Sweden and some parts of the UK. We also sell electricity, so retail to customers, both households and industry. And we have a number of new services, for example, in the area of e-mobility, heat pumps, etc. And then last but not least, we are also a producer of heat, mainly district heating. For example, in Sweden, we are responsible for district heating in Uppsala, where we have a heat plant. And then we have also in other countries, and also more in Sweden. So coming to the energy transition, what is the link there? We have a vision as Vattenfall to enable the fossil freedom that drives society forward. So we speak a lot about fossil freedom, breaking free from fossil fuels. And to make it possible to live, move, and make, make and live fossil free. I will get back to this, but you understand the concept. So move, meaning decarbonizing the transportation, make, decarbonizing industrial productions, and live is, for example, decarbonizing heating that I was speaking about, and cooking, in general, buildings. And of course, since we work on the market, then we need to, I'd say, make it a profitable energy business. But we believe that this is the case because if you look 20 years from now, there will not be probably any companies that are successful and profitable that's still dealing with fossil fuels. And we from R&D, if I speak just a minute about my function, from the R&D perspective, our role is to, of course, help Vattenfall. Vattenfall wants to reach fossil freedom. We are part of a set of strategic functions that have the purpose of accelerating the way to fossil freedom. And especially in since we work with research and development, our role is to create innovative and competitive solutions to accelerate the way to fossil freedom. And I was very happy, actually, to be invited also to this panel we will have at lunchtime, because I think there is a coupling there with working more in collaborations between industry and academia to accelerate the way. Yeah, so in short, we develop for fossil freedom, And we are about 150 people in Sweden. I will not say so much about this. We are about 145 people, and we work both with research that supports our businesses in Vattenfall. So like I said, we have a hydropower, so we have a hydropower unit, and we support them with R&D. We have a wind power unit, and we have a portfolio that supports them with R&D, etc. And on top of that, we have some more strategic topics we work on that are so new maybe that they haven't found still yet a home in our business. So that was a bit of an introduction on Vattenfall. I'm glad to take questions also on this part, but maybe you save them for the end and we take all the questions at once. And then now I would like to go more into the topic about the energy transition and how it impacts the energy system and the power system. And when I do that, often I refer to a model that I haven't invented. I think it's quite open out there. We speak often about the 3 Ds of the energy transition. And the first one is, of course, decarbonization, because this is the climate change is the biggest challenge we have in our generation, I think. And we need to decarbonize our different activities, like we said before, transportation, industry, and buildings. That means mainly going through electrification. So for us, of course, as an electricity provider, this is very good. But the point is there are 2 things. The first one is that often when you change to electricity, like in electric vehicles, the electric drivetrain is maybe 3 times more or less 3 times more efficient than combustion. So you save a lot of energy, and then you can move more cars with the same energy, right? But also, if you electrify and the energy, the electricity that you are using is produced from fossil-free sources, then you will have virtually no emissions. So that's a basic here. And we also talk quite a lot about direct electrification. You see on the left, bottom part left, meaning that we use then directly the electricity, for example, to move the car, so electric vehicles, or to heat up the buildings, so for instance, using a heat pumps. And then the name of the game here, again, is to add to the system, to get rid of the fossil fuel electricity generation, and instead add more renewables. That you see, I think, in the middle part on the top, wind power, solar power, for instance. And in Sweden, we also have quite a lot of nuclear, and we're discussing to build new one as well. But then there are also some sectors or some activities that is a little bit more difficult to electrify. And it's, for example, some of the heavy industrial processes that use a lot of electricity, but also use the fossil fuel as part of the process. So it's not as easy to just replace it, swap for an electric solution. And in that case, we speak about the indirect electrification. So what you can do is, in most cases, to replace the fossil fuel in the process with hydrogen. And hydrogen you produce by electrolysis using green or fossil-free sources. That's called then green hydrogen. Then you achieve also freedom from carbon dioxide, so to speak. Then you reduce the emissions. So I have some examples of this, and what is very interesting with this type of activities, that is clear that they need to be done in cooperation among different actors, because then it's you need to change the whole chain and the whole process behind that type of industry. So for instance, we work with jet fuel. Aviation is one of these. It's very difficult to electrify an airplane with batteries, for example. So here we're working on how to make synthetic fuels or e-fuels, so sustainable aviation fuel based on electricity. And there you use fossil-free hydrogen combined with CO2 that you capture from industrial activity. So CO2 actually becomes a resource instead of a problem. And we have a similar activity on the west coast of Sweden here with refineries there. There's some refineries in that area. And in that case, again, it's about producing aviation fuels from the CO2 from the refineries and the hydrogen. But here we couple it even stronger with where the electricity is coming from, because this becomes an issue then. If you have to do this change in industry, it's very investment heavy, to change all your process and build a completely new plant. So the industries that should do that, they are also concerned that if they do and they put all this money, then there will be no electricity, because that is becoming already an issue today. They don't know where to connect, and the grid is not enough, and there is not enough electricity. So here we couple it with the developing offshore wind power on the west coast, so that we have a match between the supply of electricity and the demand. My last example is maybe a bit more interesting for this crowd, is our hydrogen storage project, or we have a project in collaboration with SSAB, Swedish steel manufacturer, and LKAB, Swedish mining company, called Hybrid or Hybrid, about making fossil-free steel from with a direct reduction process. I will not explain all the details here, but one thing that we have been working on from Vattenfall, and especially from my R&D department, is that we have also looked at, if we make the hydrogen, can we then store it? And gas storage is relatively well known. We have 2 gas storage examples in Sweden, but when you do this for hydrogen, it's completely different. You need to redo everything. And we have built 100 cubic meter pilot in Luleå, close to the Hybrid pilot plant of fossil-free steel. And the concept is, of course, that how to say, normally we would make, you look on the left-hand side and the top one, then if we have plenty of electricity at some point during the day or a certain day we have very low electricity prices, then we can make more hydrogen than the steel plant needs, and we save it for later. And then in the bottom part you see that when the grid is more congested, then the electricity prices rises. Instead of buying the electricity to make the hydrogen, you use from the storage. Very simple concept, but then it's not so easy to do it. And we have built this pilot, and we've done 2 successful campaigns of a couple of weeks each, both in summer and in winter, to show how we can get the value of the flexibility out of the market. And of course, to do that, then we had to develop the whole control and optimization of that, including the market prices. And what you see here is that we have a relatively good, the blue curve is the actual electricity consumption from the steel plant, and the yellow is our planned operation based on the day-ahead bids. So this is going to come much more, and here control and optimization I think is very important. What we can see, we could show that we could reduce or improve the business case for building hydrogen storage by somewhere between 25% and 40%. So it's actually very significant. That was a bit about decarbonization. We could speak 1 hour only on that, of course. But now I want to go to the second D. And the second D is decentralization. And here I will zoom in a bit more on the grid and how the customers, how to say, go from consumers to prosumers. Let's see about that. So I think I see there are some people here that maybe could remember. If you are born in Sweden and you are a bit older than I am, or I wasn't raised in Sweden, but people remember maybe this very successful campaign in the 80s from Vattenfall called 2 holes in the wall. Anybody? 2 hål i väggen? Yes? Good. So, meaning that the power system was so simple, or at least Vattenfall had fixed it, so that as a user, it was so easy, you could just plug in your appliance and electricity starts to flow. And we used to have a very, at least if not a simple, but because it has always been complex, but a very vertical structure of the system with big power plants that generate electricity, for instance, nuclear or hydro, that is then fed to transmission lines that bring the power over very long distances. And then you transform down a couple of voltage levels and you distribute to the consumers. This picture here shows already from maybe in the 90s, there was a big change that was introducing the markets. So in this case, we have still a large-scale generation plants, but that they are feeding or selling into the market through a trader or through the trading arm of the generation company, for instance, in Vattenfall, into the energy market. You see that on the right. And here we start to split the flow of money, so the financial transactions from the actual grid connections. So still the generation is connected to the transmission, then goes to the distribution, etc. But then the consumer becomes customer, right? Because there is a retailer or utility that buys the power from the market and sell it. So far, I think so good. You probably recognize that from your electricity bill. But then when we go now to the more recent years, we see that this system is being stressed quite a lot. We still have this large-scale generation, but we are also adding new generation in the form of renewables. On the top left, you can see that there. For example, this large offshore wind power I was talking about, 2 gigawatts, that's as big as a nuclear reactor. So that goes into that bin. And also solar plants, we build nowadays gigawatt big in the Middle East, for instance. And also in Scandinavia and continental Europe, we have some example of anyway, large-sized plant in 100 megawatt range. So when we are adding more renewables, you know that I think already that we cannot control the source itself. So you can't control when the wind blows or when the sun shines. So that introduced some intermittency and more variations in the system. Another thing that happened is that in the past couple of years with the Russian invasion of Ukraine, we saw the gas prices go pretty much through the roof. So that also created more unrest, if you will, in the market and more volatility. So in general, we have a high market volatility. You see that on the top right, that needs to be handled. But also we have a volatility also physically in the grid that needs to be handled. The TSO, transmission system operator, for instance, in Sweden is Svenska kraftnät, but there's, of course, several, and in different countries, some countries have more than one, like Germany. But the transmission system operator is this, how to say, responsibility of keeping the balance at all times and of keeping the grid stable. And in a market-based situation, then they do that by purchasing services called ancillary services that can, how to say, they also look different depending on the type of problem you want to fix. So what is happening now with this variation and more volatility is that new issues are popping up. For instance, we have a lower inertia in the grids, and then every time there is a disturbance, how to say, the variations are more, how to say, bigger, and the system is less stable. And in order to do so, we have introduced a number of these services. Here is an example, simplified also, about the Nordic system. But I know, for instance, Ireland, that has a special situation with the islanded system, etc. They have up to 14, I think they have 14 ancillary services today. And these services can be provided by generators, for instance, hydro or others, by energy storage, or by even by the demand. If you have a big industrial consumer that can switch off a load of, I don't know, 50 megawatt or 100 megawatt. That is the easiest way to do, I would say, this type of, for example, the fast frequency response. And that requires maybe not so much control, but simpler automation, I would say. So you just switch on and off. But still, you need quite a big communication chain and exchanging data, et cetera, to make that happen automatically. Here I have one example from us, from Vattenfall. Now what happens here is that we start to build hybrid plants combining different resources also. So wind, solar, and battery storage. This is one case in the Netherlands called Haringvliet. And I think this is going to happen more and more because, of course, it improves also the business case or the profitability of the plant if you can add the storage because you get the most stable output, but also because you can provide these services that today are pretty lucrative. That may change in the future as more resources come in, but today you can make quite a lot of money. And of course, that requires quite some advanced control. You have, of course, the control at the converter level in the solar park, in the wind park, turbine, and in the battery. But then what we work more on is the optimization at the overall park level. And there I think there is a lot still to do. And it's more about how to combine and how to prioritize the different, because then you get different control objectives, right? Should you produce power for the depending on the market price, or should you reserve a certain amount of power for different services, and what services you outsay, and then implement a response according to curves like the one I've been showing. Here I was tempted to put a block scheme in, but I didn't do that. But this one actually, for those who are interested, we have published quite a lot on these hybrid plants, and we're working now also on hybridization with hydrogen. So you could combine again wind, or also in existing plants, you could make them, how to say, more fit to a flexible system by adding different type of storage. It could be battery storage, but it could also be hydrogen. And then maybe if you are close to an industrial plant that could make use of the hydrogen as an off-taker, is a much better case. Good. Now, that was a bit about the transmission system, but I think the real revolution maybe is happening in the distribution, because in distribution, in the old system with the two holes in the wall, we had completely no generation. There was only consumers. But nowadays, what happens is that with these new renewable energy sources, you can build them quite cost effectively also in small sizes. So they tend to be more and more connected at distribution level. Now, we are many people in this room. I don't know how many have solar power, solar cells on their roofs. Can I get some show of hands? Let's see. Okay, few people. Do you also have batteries? No? I do? Okay. Yeah. Well, there was very few. When I speak to electric power engineers, somehow there's more hands up. Yeah, but look it up. Okay, and then you can run around with your app and look at how much power you're producing. I do that, and compare with your neighbor, etc. So it's also fun if you are a bit nerdy. Okay. Again, now in distribution, what is different is that we start to get generation also there. But then we have also these trends that are impacting, because the decarbonization means that many customers, industrial but also households, they need more power. So it's the increased power demand or energy demand you see there on the bottom right. And you could see it also in your home if you have an electric car. And now, let's see who has an electric car. Okay, there was less than 10 people. But if you have an electric car, then you probably get a little bit of a shock the first time you charge at home, because then you realize that that is much more than your normal consumption before you install the charger. So it's quite a big increase in energy demand. And then what happens also is that the moment you and I and now all these people in the room, they will run away and implement and install solar cells next week. I'm sure about that. You can also buy from Vattenfall, by the way. But there are others. And what happens there is that then if you want to install now next week solar cells on your roof, then you have to make an application for connection. And then in the past couple of years, we had a boom of solar power, mainly, and also electric cars, et cetera, et cetera. This results in a number of applications to the distribution system operators for new connections or for increased power demand, et cetera, et cetera. So this is not much of a technical challenge, I would say, but if I should list the two biggest challenges distribution system operators have today, is two things. The first one is grid capacity or congestion. That's connected to the first point there, the increased power demand. Because then everybody needs more electric power, and then the distribution grid network is not dimensioned for that. And then secondly, the other issue is that they're totally flooded by connection requests. And it used to be handled manually because it was okay. And now it's maybe 10 or 100-fold increase, and there we need to digitalize also that process. But I don't think we need the control experts for that one. So that was just for a fun fact. But then how do we do that? What happens now is that we need then to build more infrastructure in the distribution grid, then we need to build also more decentralized infrastructure to reach all these electric cars and heat pumps to be how to say, electrified and so on. And we talk about maybe building 2-3 times the grid we have today, and that doesn't make any sense, clearly, because if you look at this volatility, you can also see that the grid we have today is not always used. The capacity factor is not so high. So you have some peaks where everybody wants electricity, and then you have other parts of the day when it's not used. So the question is more, how can we use the grid we have? We still will have to build a lot, but how can we use the grid more efficiently? And then one of the ways is what we call flexibility. And I think that's very pretty much, I know some people in the room are working on this already. We talked about this yesterday. But that's the word of the day in our energy sector, introducing flexibility or flexibility in general, both at the customer level, meaning to the bottom left, that is in households, for instance. And that is simple concept. So I shouldn't, maybe why do I have to charge my car exactly when, at this moment, when everybody else is charging, then the electricity price will be high. If I can shift my activities in time, I don't have a special place to be at a certain time, then I can charge the car during the night, for example, when the electricity price is lower. Why is the electricity price is lower? Because the grid is not stressed. So there is a coupling there, of course. And that can be used, of course, customer flexibility, but also to balance the grid at a higher level, like transmission we were discussing before. We also see emerging some bigger sources of flexibility, so that bids directly in the market, what is called the merchant flex in the slide. And typical, or one example of this could be the hydrogen storage I was telling you about earlier. That then you can bid this flexibility on the market, matching different services then. So what I would like to do now is to give you some examples of how we are working with this, often also in collaboration with others. One example here of this more decentralized approach, and that, how to say, to use these resources that are out there in also at the outskirts of the grid, if you will, is this microgrid project. We have we have done a few of those, but this is the most recent, was installed last autumn on Arolma. It's an island in the Stockholm archipelago. And actually, this island is like many islands around here. There's very few residents year-round. It's 200. But then, of course, in summer, people have summer houses, so in summer they have very high consumption compared to outside the rest of the year. But of course, in winter it's cold, so they also have high consumption for the few people that are there because it's colder. And we have one cable to the island, but of course it's really not motivated economically to build a second cable. But we would like to improve the quality of supply to the people on the island. So this fit quite nicely to test this solution. So what we're doing here is that we have installed energy storage on the island. And you may not be familiar with the microgrid concept, so I'll explain briefly. But the idea is that the microgrid is a part of the grid that works, as standard, connected to the bigger grid normally. But then in case of, in different situations, contingencies or other, it can seamless go over to island mode and then work as an island, disconnected from the main grid, and then reconnect back to the main grid whenever, the operator says so. And of course, you understand then in order to do so, you need to have either some generation source in the microgrid or some storage or a combination of both. So here we have some PV. There's PV on the island, but also we have some PV in our system with this microgrid. And we put 2 battery storages. Actually, it's not really needed, but that was to make it a little bit more complex because it's an R&D project. And mainly what we worked on is then the control, how you control the whole system to make the balance when you go from grid-connected operation to off-grid and then back. And also the protection, because then when you have a fault in the grid, then you need to be able to trip the fault, to trip the part of the grid to make the repairs, and then the rest continues to work. And to do so, then the protection needs to be set so that it works both when you are connected to the big grid, but then when you go into island mode with maybe both storages, when you go into island mode when one of the storages is not in operation, etc. So all possible operating conditions. It's quite a nice project. We also take groups on tour there if you're interested. It looks, it's still Swedish, so it looks like a Swedish red house. That's one of the battery storages. And another thing we did that is very nice is this web page. You see, it's a part of the web page on the bottom right. Unfortunately, it's only in Swedish, I believe. There you can connect and you can see in real time if the microgrid is connected to the bigger grid or not, and how much, the state of charge of the batteries or whatever. So quite some engagement from the customers there. And continuing maybe a bit on battery storage, because that's that's also very popular nowadays, very interesting. I assume there's a number of people already here that are working on some kind of control and optimization related to battery storage. Here, the thing is that battery storage is so flexible, right? So you can do quite a lot. Now I'm saying flexible, not in the way of flexibility, but a flexible resource, you can do so many things with it. So here you see, for instance, the different applications, and I take them from left to right. On the top is peak shaving, so this moving, your consumption in time to get a better, to optimize your electricity bill, really. The middle one on the top is the frequency regulation services we mentioned before, ancillary services to transmission. Then we have on the right hand there grid capacity. We also have some examples where storage has been used simply to alleviate when the grid is too congested. Then you can, for example, accept more customers if maybe those few peak hours you can cover with the storage. And then on the bottom part you have others, for example, this hybrid, so how to make the energy from renewable power plants more stable or a better profile. better power supply to industrial customers, and then in general improve, use it as an uninterruptible power supply, if you will. And we have worked with many of those and have different examples here. So I will not go through everything because of the time, but just as you see in the small icon below the picture, it connects the different applications. But maybe the one I would like to mention is this Boliden Bergsöe on the top left. It's an interesting case. So it's more and more industrial customers we see, they want to install battery storage because they see also the possibility to on the one hand, improve power quality and reliability for their own grid, but on the other hand, to use it in the bigger grid to produce ancillary services and they, improve their revenues. And similarly with the Haringfleet, what I already mentioned, with hybrid power park, also Uppsala, was the biggest one in Sweden when it was installed, and that was more for grid capacity. So there's a huge number of applications that are popping up, and battery storage is here to stay. Although maybe it could be that the market for some applications like ancillary services will saturate, but still, I think this is an application really that is, more and more interesting. How to combine different services. And maybe if we look a little bit more what's going to happen. So same story there with energy storage, distributed, we already said, in the grid, but you have a special case there, vehicle to grid. You could use the battery in your car as a source of storage. So this is now relatively not so new anymore, but still it's not implemented out there. And you can already guess the battery in the car is much bigger than any battery than the three of us here who raised their hand have in their garage. So if that happens, it can be very revolutionary for the system. And we have already some manufacturers that are offering cars that are prepared at least for vehicle to grid. From a technical perspective, it's not an issue to have bidirectional power flow in your converter in the car. All the issues are, legal and the lifetime of your battery, how it's going to be impacted, etc. But here we're working on a pilot with a number of other partners. It's the Swedish TSO. This pilot is in Gothenburg on the West Coast. With the Chalmers University, with the Swedish TSO, with the utility there, Göteborg Energy, and we from Vattenfall are working on both on the grid codes. So what are the requirements to be able to connect to the grid, and also on the business models, because to make this whole chain work, you have several stakeholders beside the car owner. That somehow, if this has to happen, then all stakeholders need to gain something. So it's quite important, that part as well. But what is interesting, I think, more from a technical perspective, is how these cars will be moving, and we don't know where they are at any time of the day, and their state of charge, etc., how you aggregate that, and how much risk can you take, that the moment you need to provide the flexibility, the cars are actually not connected where they should be, etc., etc. So, and of course, this is a case that is almost made for using AI in some way or the other to make it work. So we're coming up quickly to the end here, because now it's the third D. So we looked at decarbonization, where everything starts from the need to decarbonize the energy system because of the climate change and the carbon dioxide emissions. Then we saw that means more electricity at all levels, and this means more decentralized energy system and consumption and generation, and this need to balance. And to make everything work, I would say, in this more complex system, digitalization is not, something nice to have. It's really needed. Otherwise, we're not going to make it, really. And the point is that we get a much more complex system. I think I hope I managed to show that with all these resources that need to interact on a real-time basis, right? At any time, 365 days per year, 24/7, et cetera. And you always need to have the perfect balance between generation and consumption. So this needs to work in an automatic fashion more and more. What we get is we get a more complex system with more volatility, and also we will get more events, more disruptions in the system, and we have less time to react. So the question is how we can do this in a more automatic fashion. Here is just some examples on where there is an issue, there is also an opportunity, right? All the different things you could do with digitalization in the system. We need to have better forecasting methods. For instance, we need to forecast the load. Load models have traditionally been really bad. There is also something that you could do better, probably with data-driven approach, with artificial intelligence, etc. And the whole demand response area and so on. So these are the 3Ds, but then the question is, could we imagine a future then where it's completely, fully automated, the electric power grid? I think that's an interesting question for all of us to reflect. And that's, I think, my final slide here. So is a fully autonomous power grid possible? When you talk to the operators or the people who have been working traditionally with the power grid, everybody's very scared. But on the other end, we talk about autonomous cars, for instance, and to sit in one of those. And I would prefer to sit in that one than a car driven by somebody who is tired and has not slept, etc., etc. So maybe this is the same thing here. But some of the grid operators, for instance, Statnet, you see that picture on the left, bottom left. They say we need more digitalization, more automation. At some point, they presented also a vision of a fully automated power grid. I think they toned it down a bit more recently. On the right-hand side, you see what DAL-E tells you. I thought, okay, I need a good picture to finish, right? And then I thought, today you can make all pictures you want with these tools. So there is DAL-E 3 integrated in Bing. So if you ask them about a picture of the fully autonomous electric power grid, that's how it looks like on the right-hand side. I think that we will not see exactly that in 2050. There is more to talk about. We have not talked about AI. Again, when can we trust it? Could we use it for this, automating the power grid completely, and the operator just looks and has the possibility to stop things if they're going wrong? We have not talked about cybersecurity. That's also a big topic. If we go for a more and more automated grid, then of course there are risks and it's critical infrastructure. If foreign powers would get into the control room and be able to switch off the whole power grid, of course that's a very scary scenario. And maybe there's more things that you can ask me about in the remaining 5 minutes. That was it, I think. Thank you.
Thank you, Ambra, for this excellent presentation. So, questions? Yes. Where do we have a microphone? It's coming up there. Just wait a second.
Microphone is running quickly down.
Thank you for a very nice presentation.
Did you actually hear that? I don't know if it's on.
It's on the screen.
It's on now? Okay,
yes.
Thank you for a very nice presentation.
Thank you.
So we're understanding that balancing is needed more and more with more renewables. And of course, there is a cost for building it, maintaining it, and operating this balancing. And is there an upper limit on how much renewables we can have before it's become non-profitable? And what is currently the cost for the balancing in our electricity bill, for example?
Okay. I don't have the number now in my head, but that's the million-dollar question you are asking. What is the highest, percentage of renewables? It's also like this. I'm sorry to say, it depends. But for instance, if you compare, it depends on the old system. So if you take that on country level, that is not exactly correct, because what is important is the size of the fully interconnected system. So Denmark, for example, has, I think, already more than 50%, but of course they are it was a bad example because part of Denmark is part of the Nordic power system and part is part of the continental Europe. But what plays a role there, of course, is the size of the total system and the total inertia of the total system. But again, there are countries like Ireland that don't have a good situation from that perspective, don't have a big interconnected system with a high inertia, etc. And still they've worked quite a lot with battery storage. They were very early introducing it. And by that, they could increase their wind power more or less around 50%. So maybe one of you could study the theoretical upper limit, but I think we can go. We can definitely go very high with more digitalization. I think that is really the key. We did maybe one last thing. We did a project with when I was in DMV just a few years ago. It's publicly available. We did a project with Norwegian TSO with Statnett about using system protection schemes in the Nordic system and how that could improve the reliability. And I think you can do a lot with more digitalization and automation, because then you can somehow also start to question really the design criteria we have been using before, like N-1 typical, that you have to withstand one fault of a critical component. With that project, with the SPS, we could show that yes, if we have one fault with a critical component, we could also actively separate parts of the grid with this system protection and keep working. So I'm technically optimist that we can go further than that. There's Alf, did you see that? And I don't know if there's more. Do you see them? There's a hand there.
Up there, please.
Yeah, the microphone is on its way.
Okay.
Oh, there was another microphone.
Oh, okay. Please go ahead.
Thank you for the very engaging talk. Your last photo from Dali is absolutely terrifying. And my question, in fact, is about AI, but data centers specifically. So the question is, there's a lot of international discussion about extreme load growth from data centers because of AI. I understand in Sweden that demand has remained flat for the past 40 years. The question is, does Vattenfall expect a lot of load growth from data centers? And if so, what is the strategy to achieve that while maintaining decarbonization, flexibility, resilience?
Thank you. Great question. Okay, there's several aspects here, but I should say we have seen this growth. I've also seen it before. Oh, be careful. I've also seen it before I joined Vattenfall. We've seen this growth of data centers getting into 200, 300 megawatt. Now it's even more. It is an issue. Two points there. First one, the data center developers themselves, they are not stupid, so they see this debate about their growing energy consumption, etc., etc. So they are doing also themselves quite a lot now to secure, first of all, green electricity to their data centers, and also to explore options for providing more flexibility to the grid, to become, some of them express it as to become a better citizen of, a good citizen of the grid. So I think that there is an awareness there and how to say, willingness to improve. This is one part. Then I think you were saying, especially on AI, I've been talking about this just, I think, last week or 2 weeks before with one of these data center developers. And what was interesting is that that type of how to say, operations or actions, they are less time critical. So they are easier to shift in time, they were mentioning. So I think that's also an interesting aspect, that they can contribute to that flexibility. Because traditionally, we're used to see the data center as a constant power load, pretty much. But what they were saying is that this is not really the case when more AI comes in, because it's less time critical. You could split the calculations, or how to call it, in time better.
Thank you for a very delightful and most insightful lecture. You were presenting a vision of storing hydrogen, storing when the electricity price was low, retrieving when electricity price was high. So my question is, do you intend also to use the heat from that process? And the background for my question, if you look from physics, there's a limitation to the round trip efficiency. It's difficult to get numbers higher than 30–40%. So you could only make that economically sustainable if you have a price variation of a factor of more than 2.5. So have you other ways, like using the heat, or can you comment on how you see that as a sustainable business model?
So I haven't studied that, so I cannot comment on the 2.5. But what I can say, I normally mention, this time I didn't, that also I think in general in the system going forward, we see this more and more, you have heard the word, I'm sure everybody, sector coupling. So I used to say that in previous times, we have almost the luxury to say, like, I deal with electricity, the guy works with heat and the other guy works with transport. Now it's not like that anymore, right? Or it's not going to be, because in 20 years, if we have one electron, then we need to think what is most better for society or for my private economy, to charge my car, or to make fossil-free steel, or to make hydrogen, to make fossil-free steel, etc., etc. So it's all much more coupled. I think what I see is that from also we work a lot with heat as well, and there we look, not only us but everybody in the sector looks much more at how to use the energy better, so to use the waste heat from the industrial processes, but also from nuclear, for example, or from other generation, to do something with that, so to speak. Then I recognize that when we talk about flexibility and transience, etc., then of course there could be physical limitations. But we look more and more into this, and not only us. I think
I think we are running out of time, so
I will be around today. So if you
have time for one more question.
Yeah. Oh, sorry for that.
I have a question. So in the US, the picture is maybe slightly different. Department of Energy has been investing very heavily in sort of strategic resource of utilizing the coal. No wind is blowing, no sun is shining. What do you do then? And then there has been a lot of work in cleaning up the coal consumption. So for example, chemical looping. So and there has been also Alstom Power involved in that. And now it's GE Thermal. Yeah. So I haven't seen anything in your presentation related to that. Do you view it as a viable resource, or it's completely out of interest of your company, and in general you don't see anything there for Swedish powered grid?
I'm sorry, I was already starting to respond, so I didn't hear the last. You said
okay. Yeah. I wonder if you see any opportunity for Swedish power grid in utilization of clean coal technologies.
Like carbon removal,
looping,
for instance?
Yes.
Or carbon capture and storage, for instance?
Not that much carbon capture, but really chemical looping type of thing, where the process is that you produce completely emission-free electricity with just trickle of CO2 and some sludge, and there is no CO2 emission into the air through chemical looping. Like it's a solid oxidizer technology, unlike the gas oxidizer with oxygen.
I'm not sure I understood fully. So you're talking about chemical?
Looping technology, chemical looping.
Two of you
Yes.
probably
No, I'm
sort
sorry.
this out during
it
the
could
break.
be a nomenclature that maybe is more US specific, and then I'm afraid I didn't understand you.
Okay.
Sorry for that.
So thanks a lot.
Thank you,
again,
everybody.
Anna.
Thank you.